Welcome to Ask and Learn.
We are asked to answer a question about the average number of comparisons made by the quicksort algorithm. So we're told that it can be shown that Cn, the average number of comparisons made by the quicksort algorithm, when sorting n elements in random order, satisfies the recurrence relation Cn equals n plus 1 plus the sum plus 2 over n times the sum from k equals 0 to n minus 1 of ck for n equals 1, 2, and so on, with the initial condition that C0 is equal to 0. In part A, we are asked to find a different recurrence relation which Cn satisfies. So, in part A, we have that NCn minus n plus 1 times Cn minus 1 this is equal to n times Cn minus n times Cn minus 1 minus 1 times Cn minus 1 which is the same as n times Cn minus n minus 1 times Cn minus 1 minus 2 Cn minus 1, and using the formula we're given for Cn, this is equal to n times n plus 1 plus n over 2 times the sum from k equals 0 to n minus 1 of ck minus n minus 1 times, and again, we use the formula n minus 1 plus 1 is simply n plus n minus 1 over 2 times the sum from k equals 0 to n minus 2 ck my mistake, this should be, instead of n over 2, 2 over n. So this should be plus 2 over n. And this should be plus 2 over n minus 1. And then subtract 2 Cn minus 1. And this is equal to n squared plus n plus 2 times the sum from k equals 0 to n minus 1 of ck minus, and then we get n squared minus n and minus 2 times the sum from k equals 0 to n minus 2 of ck minus 2 times cn minus 1. And so we get n squared minus n squared is going to be 0, n minus n is 0, and then we get 2 times k equals 0 to n minus 1 of ck minus 2 times the sum from k equals 0 to n minus 2 of ck is going to give us 2 times cn minus 1 minus 2 times cn minus 1, which is simply 0. Or instead of 0, it should be the n's don't cancel out, they actually add, so I get 2n plus 2cn minus 1 minus 2cn minus 1, which is 2n. And rearranging, I get ncn is equal to n plus 1 times cn minus 1 plus 2n for n greater than or equal to 1. So here's a recurrence relation. And in part B, we're asked to solve this recurrence relation to find an explicit formula for C of n. So notice that the recurrence relation from part A is a linear, non-homogeneous recurrence relation with variable coefficients. And recall from a previous problem that if we take f of n to be n, g of n to be n plus 1, and h of n to be 2n, and we take q of n to be f of 1 times f of 2 up to f of n minus 1. Looking for a towel? Yeah. Let's see if we have any. An extra toothbrush. Do you have an extra toothbrush? No, I don't think so. Excuse me. So then this is that over g of 1 times g of 2 times g of n. Then by a previous problem, and also we have that our initial condition is 0, we have that C of n is going to be equal to the initial condition 0 plus the sum from I equals 1 to n of q of I times h of I all over g of n plus 1 times q of n plus 1. And now, to figure out what q of n is, you have q of n is going to be, well, this is f of 1 is just 1, f of 2 is 2, all the way up to f of n minus 1, which is n minus 1. And then the denominator, we have g of 1, which is 2, g of 2, which is 3, all the way up to g of n, which is n plus 1. And so we can cancel out terms so that we get, in the numerator, 1. In the denominator, we have n times n plus 1. And so it follows that C of n is equal to the sum from I equals 1 to n of q of n, which is 1 over n times n plus 1. And then what was h of n. h of n is 2n, so this is going to be 2I over I times I plus 1, all divided by g of n plus 1, which is going to be n plus 2, times q of n plus 1, which is going to be 1 over n plus 1 times n plus 2. This reduces to 2 times the sum from I equals 1 to n of 1 over I plus 1 and all over 1 over n plus 1, which can be rewritten as 2 times n plus 1 times the sum from I equals 1 to n of 1 over I plus 1. And this is our answer.